This is 2.5, dealing with linear functions and models of linear functions. So first of all, linear function, a lot of you guys should recognize it already, is in the form of y equals mx plus b. As a function, it's written as f of x equals ax plus b. So you're already familiar with that, and you've got the slope of m, or in this equation, a, and the y-intercept of b. So the first example is determine if the given function is linear. So we just have to see if it's in y equals mx plus b. So we can, just by looking at this, we can see that that's y equals 3x plus 2. And yes, so that is y equals mx plus b. Using the distributive property, we can see that this is going to be 3. Y equals 3 minus 6x, which is the same thing as y equals negative 6x plus 3. So yes, it's in y equals mx plus b. If we use the distributive property on this one, notice what we're going to get. We're going to get y equals 4x plus 3x squared. So we can see that this is not a linear function. This is actually a quadratic function. And the same thing here, if we take, divide individually here, so you're going to get 1/4 minus 5/4 x. And again, if we write it in exact form, so negative 5/4 x plus 1/4. And so yes, that would be in y equals mx plus b. And just in general, by the way, I know these say f, g, h, and k. I'm just in the generic form putting it as y equals mx plus b. All right, so slope and rate of change. We talked about the rate of change and slope in the last section. So again, solving for slope, we're most familiar with y2 minus y1 over x2 minus x1. The correct notation in function form is the f of x of 2 minus f of x of sub 1, then divided by the x2 minus x1. We also learned this, that's the same thing as the average rate of change. So slope and average rate of change is the exact same thing. So if you look at example 3, a dam is, look at this word problem here, a dam is built on a river to create a reservoir. The water level in the reservoir at time t is given by this. So this is the function that the water is taking place at this dam. And so what we want to do is A, sketch the graph, and notice you can easily sketch this, but I do want you to point out, I do want you to notice it's in, we got t as the x-axis, so we got y. As the water raises, the function is based on time, so f of t. So I just want you to notice the notation of this. So we are sketching that function. So what is the slope of the graph? Well, once you notice that the slope is in y equals mx plus b form, so we can see that the slope of the graph is 4.5. So notice letter C though. So letter B says, what is the slope? Letter C says, at what rate is the water level in the reservoir changing? So remember the last slide that we talked about is the average rate of change is also the same as the slope. So this is basically just the interpretation of this. So notice the slope is 4.5. So notice what this is talking about. T is the number of years that the dam was constructed in feet. So notice it is rising. The water level is rising. So it's increasing 4.5 feet per year. So that's the water level of taking place in that river based off of the rate of using y equals mx plus b. All right, so let's look at this. So there's nothing really to do here, except I want you to observe the way that these functions are looking at, and notice this, like this first one talks about the amount of gas as a function of time. And so does the second one, but notice this is the tank being filled. So as you're adding the tank, you're adding gas to the tank, notice based on minutes, so 1 minute, 2 minutes, 3 minutes, and then the number of gallons. So you got to pay attention to the charts. And I want you to notice the slope of this. So we got rise over run. So you can see that the slope is 2 gallons a minute. So 6 over 3, and then reduces to 2 over 1. So 2 gallons minute, the slope of the line is 2, so the rate of change, so the rate and the slope are the same, so it's 2 gallons per minute. Likewise, on the second one, the tank is being drained, like you might have the gas on, grilling something or fireplace or whatever it is that you're doing, and notice it's being drained at a certain rate. And again, you can do this by notice that its time is in minutes, so 20 minutes based on gallons. And so you can see that it's rise over run, so it's rising -3 over 100 minutes, or they put it in decimal form, but 0.03. And notice the negative is the slope, but notice what we're talking about being very specific on the rate. The rate is it's being drained or taken out or used at 0.03 gallons per minute. So that's what we're looking for as far as the rate. So be very specific with your labeling. All right, making a linear model from a rate of change. So here, water is being pumped into a swimming pool at an average rate of 5 gallons per minute. So if you're filling your water, you're filling water into your pool or taking it out, whatever. I have to do this well, not every, but almost every winter. I have to drain my pool. Every winter I have to do that. But then every spring, when I open up my pool, sometimes I don't need to add any water at all. It's already filled up from the snow and the rain. So here, notice the water is being pumped at the rate of 5 gallons per minute. So initially the pool contains 200 gallons of water. So notice this is important. So if you notice that we're talking about, if you keep thinking of y equals mx plus b. Okay, and this is your slope or your average rate of change, and your b is your y-intercept, so your starting spot for this. And since we're talking about the function v, so this is v of t. So again, based on time, so anytime t, so v of t, so use the correct notation. And notice that it's 5 gallons per minute. So we have 5t, and then plus the initial amount, which is 200. So find a linear function. So that is letter A. So and then letter B says if the pool has a capacity of 600 gallons. So we basically want to know the maximum that you can do is 600. So we want to find out the amount of time it will take to fill it up that, and it's 600. So we just have to end up solving for this, and we're going to end up getting 80. So notice it takes 80 minutes to fill the pool up with water at that rate. So let's look at one more example, and this one we need to look at it because there's several questions. We want to look at this nice and thoroughly. This is a very good question. John and Mary are driving westward along I-76 at constant speeds. Again, if it's constant, you know it's a linear function. So the graphs in figure 5 show the distance in miles. So we got miles in that they have traveled from Philadelphia at time X. So we got, this is your time, and this right here is miles. Okay, and this is time in hours. It does say that. And this is very important. 0 corresponds to noon. Okay, so this would be literally 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, and so forth. So since it's noon. So it does give you the information, and pay attention to all those details. So and it says, note that at noon, John had already traveled 150, which you could see that right there. So initially, John had already been traveling. And I want you to notice a couple things. So letter A, notice the question. So notice the question, we got John and Mary. So let's look at John first. So if we specifically look at John, and notice the 2 points that we have from here to here. So we literally want to do rise over run, or you can literally think of it as points. So this would be like the point 4, 350. And this would be the point 2, 250. So you can do it as points if you want, or you can literally do it as rise over run. Either way, we need to find the slope that John did. And notice, once we calculate that, we're going to get John's speed as 50 miles per hour. So again, it's rising 100, and it's going over 2 hours. So 100 over 2 is 50 miles an hour. And if we do the same thing with Mary, and again, between those 2 points, you could do the exact same thing to be able to do that, but you're going to end up getting Mary's speed as 75 miles per hour. Again, calculate the rise over run, or look at the 2 points that they give us, and then calculate the slope between those 2 points. Notice that Mary is traveling faster than John. Okay, so at what speed are John and Mary traveling? We answered that. Who is traveling faster? Well, we just answered that. How does this show up in the graph? Well, notice it's showing up in the graph because notice Mary's rate is going faster. She's climbing faster on the constant speed. She's climbing faster than John. Even though John started like ahead of her, but they're going to end up meeting here, and then Mary will end up passing John as well. So letter B, find functions that model this distance that John and Mary have traveled. Well, notice John's, let's look at John's, y equals mx plus b. So if we notice that, we're going to have two different things. So if we call, let's call this function f and g. Okay, yeah, it doesn't tell us which function, what to call it. So we get f of x, because they're telling us of x. So f of x would be 50 miles per hour. I keep saying time, but it's actually of x. So 50x, and then notice John started at 150. That's John. And then notice Mary, we're going to say g of x, is 75. Her rate is 75 miles per hour. And then she started at 0. So we can put plus 0 there if we want to, but that's the two functions. Now, letter C says, how far will John and Mary have traveled at 5 p.m.? Now, remember they started at noon, so we're talking about 5 hours of travel time. So f of 5, so we're going to substitute 5 into the f function, which is John's. So if we substitute 5 into that, we're going to end up getting 400 miles. And then the same thing with Mary. So if we take g of 5 and we substitute g of 5 in, we're going to end up getting 375. And you can see at 5 hours, you can literally see this as you kept graphing this, and you go like g of 4, g of 3, g of 2, g of 1. You can see each one of those. You can actually see where they're located on the graph if the graph went further, because like 5 would be right here. All right, so you can see it on the graph as well. So they're not, Mary hasn't quite caught up with John yet to be able to do that. So for what time period is Mary behind John? Will Mary overtake John? If so, at what time? And then lastly, it says, for what time period is Mary behind John? So what we need to find is when eventually they're going to meet up with each other. They're going to, Mary started off behind John and was traveling for a certain amount of time. We want to find out when Mary will actually end up catching. And so we're going to find out when they're equal to one another. So we're just going to take those two equations and set them equal to each other. Because we want to find out when they will equal. And once you do this, you're going to end up getting x equals 6. And so what that means is, notice they started at noon, and at 6 o'clock, 6 hours later, they will actually meet up. So if you actually continue the graph, like if you continue this graph, you'll see that the lines actually meet up at 6, which is at 6 p.m. And any time after that, at 6 p.m., they will meet up, and after that, 7 o'clock, 8 o'clock, then Mary's going to be in the lead following that.